Hi, welcome back. Today we're going to be talking about limit laws for combinations of functions. We have two functions. The normal situation will be they'll have a domain of the complex numbers and a range of the complex numbers. But here I'm taking the domain to be an arbitrary metric space. So X is an arbitrary metric space. They have defined limits, and the limit of f of x is going to be a, the limit of g of x is going to be b. And then we're going to combine the functions. We're going to look at the function f plus g, or f minus g, or f times g, or f divided by g. These are four typical arithmetic combinations. And this is an abstract statement here that addresses all of those at once. So box stands in for plus or minus or times or divided by. Box is a binary operation on C cross C, and it's continuous at AB. Actually, if this is divided by, then it's not defined on the entire domain here, but I'm sweeping that under the carpet. So here we have a continuous operation. And what we're trying to show is that the limit of the combined values of the functions is the combination of the two limits. Now, don't usually recap from last time, but in the last video, we proved this, which is going to come in handy right now. We proved that if a function g of x has a limit of f of y, and an outer function f is continuous at that value, why not? Then the limit of f of g of x is f of the limit of g of x. This allows us to transport a continuous function f outside of a limit, provided that that function is continuous at the limiting value here, which is what we're calling y naught. Okay, so this is going to come in handy today. So here we're dealing with this abstract version of this limit law for arithmetic combinations of functions. And let's go ahead and prove this. So proof. We have this limit defined and we have this limit defined, and we have two functions from x to c. What we're going to do is we're going to make this do the work for us. We're going to take the two functions and we're going to combine them into a third function, which is not f box g, but just f comma g. So let's let f comma g denote the function. So f comma g has a domain of x and a range of c cross c by the rule f comma g of x is going to be f of x, g of x. Basically, I have two functions, f and g, and I'm tying them together. Each one gets to be the coordinate. The f of x gets to be the first coordinate of this function. G of x gets to be the second coordinate of this function. This might remind you of parametric functions in a different context. So we're just creating this function f comma g, which maps from x to c cross c. And then I'm not going to prove this. This is basic topology. The function f comma g has a limit as x approaches x naught, which is equal to the limit a comma b. So the right way to write this is the limit as x approaches x naught of the function f comma g evaluated at x is equal to the ordered pair a comma b. So in simple language, as you apply the function f comma g to x and let x get close to x naught, the first coordinate gets close to a, the second coordinate gets close to b, and the limit of this combined function is the ordered pair ab. Okay, so that's interesting. Well, we also have box. So notice this box, whatever it is, this arithmetic operation is assumed to be continuous at a, b. So box is continuous at the point a, b. And if we think about this carefully, we are actually already in the situation described here. So we have a composition of two functions, and well, we have two functions that can be combined. The letters f and g don't match the letters f and g here. In this setup, the interior function is called g, and it is assumed to have a limit. The exterior function is called f, and it is assumed continuous at that limit. In this setup, the interior function is this combined thing, f comma g, and notice that it has a limit, namely a comma b. The exterior thing is this box, and it is actually assumed here continuous at that. And so what that means is that we can invoke that. So therefore, what do we get from this? We get, well, I'm just going to sort of copy this as it is. So the limit as x goes to x naught of the box of the function g, f, the function fg of x. So here I've got the exterior function evaluated at the interior function is equal to, so that basically I've copied this portion where f is taking the place of the box. So the box is standing in for f, and the interior f comma g thing is taking the place of the g. So I've copied that down. Well, it's equal to this, right? So that's equal to the exterior function, the box of the limit of the interior function, which is, again, the function f comma g evaluated at x. But this limit is known to be ab. So this is actually the box of a comma b. And now let's figure out, now I've written this box notation in prefix notation, but if it's that is box of a pair, but if it's an algebraic operation or an arithmetic operation, then it should probably be written in infix notation, like f of x box g of x. So let's rewrite it in infix notation and see what happens. So this thing is the box of a comma b, which is nothing more than a box b. And this thing is the limit of the box of fg of x. Well, fg of x is f of x g of x, and the box of that is simply f of x box g of x. And so we get that the limit of f of x box g of x is equal to a box b, which is exactly what we were trying to prove.